Geological research using rock and ice cores shows that the Earth's average sea level has risen by over 125 metres since the middle of the last ice age, about 20,000 years ago. Sea levels have stayed almost the same for the last 8,000 years, though. But just over a century ago, they started to rise again. They have risen by over 7 centimetres in just the last 20 years alone, the same amount they increased over the previous 60 years. We've been measuring sea levels accurately with tide gauges since the 1600s, and now satellites provide far more coverage. They show that some regions have experienced a greater rise than others. In Europe and the east coast of North America, levels have risen over 3 times more than the global average. Sea level rise has a number of significant causes. For example, melting glaciers and land-based ice sheets, and the volume of oceans expanding as they've heated up. The latter occurs from a process called thermal expansion. Over time, this heat is released into the atmosphere. This means that the melting ice sheets are likely to be the main contributing factor to sea level rise in the future. Sea ice is melting too, but like an ice cube melting in a drink, it barely affects the level. Although the recent rise can be measured in centimetres rather than the metres of the distant past, it is already having an impact on low-lying coastal regions. This will be felt elsewhere in the future. Predicting sea level rise is complex, but the last time Earth's global temperature was similar to today, 125,000 years ago, the sea was at least 5 metres higher than its current level. Could this happen again as the full effects of climate change pan out? How high the sea level rises depends on how much the Earth warms. The future projections give us our best estimate of what is likely to happen this century. The temperature of the planet is rising, but in some areas it's rising much more than others. The Arctic is warming more than twice as fast as the rest of the world. It's only recently that people have begun to understand properly what's causing this polar amplification, and it seems to be a combination of several reasons. As ice and snow melt due to rising temperatures, more of the dark surface underneath is revealed. This allows the land and ocean to absorb more heat, causing yet more warming in a feedback loop. This locally exaggerates the warming caused by greenhouse gases. It's now known that other feedback loops also exist, caused by more complex factors involving how the atmosphere behaves. But currently, polar amplification seems to be happening far more in the Arctic than the Antarctic. Why might this be the case? It's thought that the ocean around the Antarctic tends to dampen the effect, whereas the reverse is true for the Arctic. Ocean currents carry heat from the tropics northwards, exaggerating the heating effect in the Arctic. The Antarctic ice sheets have a major effect too. They're several kilometres thick and act as a giant blanket, insulating the continent from warming effects elsewhere. Additionally, the strong surface winds found at high elevations limit the warming by redistributing cold air to coastal regions. None of these factors are present in the Arctic, and there, polar amplification is very noticeable. But does it affect the climate? Some scientists have found evidence that it can weaken the jet stream and lead to an increase in extreme weather, such as flooding and drought, but this is currently an area of active research. All life on Earth is part of an intricate web of species that rely on each other for survival. If any are threatened, it risks upsetting the balance, potentially also threatening our survival. Yet it's thought that 1 million species currently face extinction. Species are becoming extinct 100 times faster than in pre-human times. In the last 50 years, the thousands of populations monitored by the World Wildlife Fund have declined on average by over 69%. If this decline continues, it will have a dramatic effect on us, with loss of livelihoods and threatened food supplies. So, is the current loss of biodiversity caused by climate change? Well, actually, the majority is caused by natural habitats being destroyed by changes in land use. But biodiversity and climate change are very closely linked. Deforestation, for example, reduces both biodiversity and the ability of the planet to absorb carbon dioxide from the atmosphere, leading to rising temperatures. These rising temperatures can lead to further biodiversity loss. A good example of this is what is currently happening to coral reefs in many parts of the world. Coral reefs are the foundation of unique ecosystems, home to many types of marine life. Corals are marine animals, similar to sea anemones and jellyfish. But unlike them, they secrete hard calcium carbonate exoskeletons that, over many years, grow into giant reefs. The biggest collection is the Great Barrier Reef in Australia, which is the largest structure made by living organisms. Corals typically feed off microscopic plants called algae that in turn need the corals to survive. It's the algae that give the corals their vibrant colours. In front of you is a life-size replica of a real coral reef, made using advanced photo-scanning techniques. Some of the corals are brightly coloured as normal, but many here have lost their colours altogether. They are victims of what is known as coral bleaching. Rising ocean temperatures cause the algae to release toxins, and the corals have reacted by expelling them. With the algae gone, the corals turn white and often die, threatening the ecosystems that rely on them. Recently, bleaching events have become increasingly common, and corals have died on a massive scale in many parts of the world. The reef here was a victim of a major mass bleaching event in 2016. The scan used to create this model was taken in 2022. Some of the flat table corals are now regrowing, but it's thought the next time a similar event happens, they'll be wiped out completely. Reefs recover, but it can take many years and will happen only if water temperatures allow. As the planet warms, an increasing number of ecosystems are likely to become threatened. The more rapid the warming is, the less likely it is that nature will be able to adapt. If that warming goes beyond 1.5 degrees Celsius, it's thought that climate change will become the biggest contributor to biodiversity loss. The sun is the most important energy source for life on Earth and is fundamental to its weather and climate. The amount of energy we receive from the sun varies naturally over time, so could this variation be contributing to our current rapidly rising global temperatures? Let's take a look at the science and find out. Since the 1970s, satellites have been used to provide accurate live monitoring of the sun's energy, but clever techniques using ice cores, for example, give us information about the sun's activity for thousands of years back through history. This shows us that the sun's activity cycles over time, repeating about every 11 years. At its peak, there's an increase in sunspots and solar flares, with spectacular aurora displays in polar regions. This graph shows us that while solar activity peaks and troughs, the planet has continued to warm regardless of this cycle. Extended periods of low sunspot activity can help explain extended cold periods in some regions, such as the Little Ice Age in the late 1600s. But scientists agree that recent trends in global average temperature rise are much more widespread across the globe and cannot be explained by this 11-year cycle. In fact, recent solar cycles have actually shown a lowering in activity, suggesting that rather than causing the recent warming, it would instead be a factor for cooling. We may even be heading for what scientists call a grand minimum of solar activity. But studies have shown that while this might cool the planet as much as 0.3 degrees Celsius, this would, at best, slow down but not reverse human-caused global warming. A much more dramatic effect on the global climate is caused by the cycle of the Earth's rotational axis and orbital path around the Sun, causing the climate to slowly change over thousands of years. In fact, it's sufficient to push the Earth in and out of glacial periods when ice sheets cover large portions of the planet. The last glacial period finished around 12,000 years ago, and currently, the orbital cycles should be causing the Earth to cool again very slowly over thousands of years. This is the opposite of the planet's current rapid temperature rise observed over a much shorter time. So we know that neither the planet's position relative to the Sun nor the solar energy cycles are responsible for the rapid warming of the Earth we see today. Can volcanoes affect our climate? Volcanic eruptions can certainly emit huge quantities of material into the atmosphere, but ash falls quickly back to Earth, and the amount of carbon dioxide emitted from even the largest historic eruption is hundreds of times less than our yearly emissions from burning fossil fuel. Volcanoes also release sulfur dioxide, and that's a different matter. If the eruption is large enough for it to reach the stratosphere, the sulfur dioxide converts into tiny particles called aerosols that remain suspended there. These reflect the sun's energy back into space, which cools the planet. This is what is registering on the graph you can see here. The peaks coincide with major eruptions, and the most significant was the Mount Pinatubo eruption in 1991. It ejected more sulfur dioxide than any eruption since Krakatoa in 1883, and it's thought to have cooled the planet by 0.5 degrees Celsius. The effect on the climate only lasted about 3 years, however, and it didn't reduce the long-term trend in a significant way. Our oceans cover more than 70% of the Earth's surface, and the influence they have on the climate is enormous. They absorb around a quarter of all carbon dioxide emissions and store huge quantities of heat, which become redistributed by ocean currents around the world. Oceans have absorbed over 90% of the heating caused by the recent greenhouse gas increase. The top few meters alone store the same amount of heat as the Earth's entire atmosphere. The ocean's heat content has been measured accurately since 1955, and the graph here shows the change in heat for the first 2 kilometers of depth. As you can see, it's steadily increasing year by year. The amount is almost too big to comprehend. It's more than every human on the planet continuously using 40 1-kilowatt microwaves simultaneously to boil the ocean. This has a large effect on the planet. The heat is a source of energy for storms. Tropical cyclones can gain more energy, becoming more intense or developing more rapidly as the oceans continue to warm. Corals become bleached, leaving them vulnerable to disease and ultimately death. This destabilizes marine life and local human populations that depend on the coral's ecosystem. Sea ice melts, causing less heat to be reflected back into space, making the sea heat up even more in a vicious circle. As the oceans warm, the water expands, causing the sea level to rise. Changes in the heat content of the oceans happen much slower than in the atmosphere, and this has a stabilizing effect on the Earth's overall temperature. But it also means that attempting to reverse or even reduce the current increase would take thousands of years. People who live in places that have cool, damp weather conditions often welcome heat waves, but for many parts of the world, they are greatly feared. As the global average temperature increases, the threat is likely to become more widespread. But what exactly is a heat wave? A heat wave usually happens during the warmest months of the year. It typically relates to a period where day and nighttime temperatures over consecutive days are significantly higher than the seasonal average. The strict definition of a heat wave usually varies from one country to another, depending on the local ability to cope with the temperatures. Heat waves often form when a particular weather pattern becomes stuck, with the usual cloud and rain being deflected away. This can last for days, or sometimes even weeks. Heat waves are often closely linked with a lack of rainfall and dry conditions, which can put extra stress on vegetation and ecosystems. Normally, some of the sun's energy is directed into evaporating water from damp ground, reducing the sun's heating effect. But when the ground is dry, the sun can heat it directly, and this strengthens the heat wave in a vicious circle. Prolonged hot and dry weather also dries out vegetation, increasing the risk of fire, as well as the chances that if a fire occurred, it would spread quickly. This is what happened in Australia at the end of 2019. Long, intense heat waves can have a major impact on melting glaciers too, destabilizing their structure and increasing the chance of flooding. It's not just the natural world that's affected by heat waves. They can also have a dramatic effect on society. Sadly, they're often associated with higher than normal mortality rates, especially for the very young, elderly, and vulnerable. The threat to water supplies is obvious, but there are other consequences. For example, the extra demand for air conditioning can lead to electricity blackouts. Transport infrastructure can become damaged, and when major rivers run dry, trade routes can be threatened. So far, we've been concentrating on the effects of heat waves on land, but our oceans can also suffer what's called a marine heat wave. Long periods of time when hot weather, low winds, and strong sunshine can cause heat to build up in the top layer of the oceans. Marine ecosystems are often sensitive to water temperature, and prolonged or intense marine heat waves can have catastrophic consequences. Coral bleaching is a notable example, as occurred when an intense marine heat wave took place in 2016. As the planet continues to warm, heat waves are generally becoming more frequent and intense across the planet. This poses an increasing threat to society and the natural world. Without advances in technology, some regions could become uninhabitable for humanity. A drought happens when drier than normal conditions occur over an extended period of time. Reduced rainfall or a lack of fresh winter snow disrupts the normal availability of water. Soils can then dry out, and the rivers and reservoirs can become too low to supply crucial irrigation water. Crops can then fail, causing a food shortage. This can ultimately lead to malnutrition and increased rates of infectious diseases such as cholera and typhoid fever. Low river levels can also disrupt transportation and power supplies, impacting economies. Extremely dry conditions often increase the risk of wildfires and dust storms. Millions of people are affected by droughts every year, and they can happen anywhere in the world. Some droughts can develop very quickly, as happened in Midwestern North America in 2012. It had more than a $30 billion impact on agricultural production. However, most droughts occur over much longer periods of time, years or even decades, when whole populations can be forced to migrate elsewhere. The worst drought of the 20th century happened in East Asia between 1928 and 1930, when many millions of people died of famine. High temperatures increase evaporation, making droughts even worse. But some plants are able to tap into water from deep underground to stay alive. Crop irrigation can help reduce the effects on agriculture, but there is a risk of using valuable water that's needed elsewhere. It comes as no surprise that a warming planet is likely to increase the chance of droughts. The increased evaporation rate can make them more intense. Reduced winter snow and ice in cold regions will also mean less meltwater in spring and summer. How badly this increase will affect us will depend on our ability to cut greenhouse gas emissions and manage water supplies. But it's thought that around a third of the Earth's land area is expected to suffer from at least moderate drought by the year 2100. Even so, other areas may actually see a reduction of droughts in the future due to local increases in rainfall. Floods can play an important part in the natural world, but they can be very disruptive and dangerous. So, is climate change making them worse? Before we answer this, firstly we need to look at the different types of floods. Some are caused directly by human activity, such as badly designed urban development or poor water management. For many areas, however, the effects of a changing climate pose the most serious threat. It's well known that as the planet warms, snow and ice melts, and sea levels are expected to rise. By the end of the century, over 400 million people are predicted to be living in areas less than 2 meters above sea level. This makes them very vulnerable to coastal flooding. The most severe form of flooding is caused by storm surges. But what are they, and why are they so dangerous? They occur when storms create strong winds over the ocean, forcing the water to build up. High tides and the low pressure of storms can make them even worse. This is what happened, for example, in 1953, when severe floods occurred around the North Sea, affecting the Netherlands, Belgium, and the UK. The most extreme storm surges generated by tropical cyclones, when sea levels can sometimes rise many meters in just a few hours. It's not surprising they've caused some of the worst natural disasters ever recorded. For example, flooding in the Ganges Delta in South Asia by the Bhola cyclone in 1970 killed hundreds of thousands of people. Unfortunately, climate change is likely to make storm surges worse. As the surface of the oceans warm, these storms can pack an even more powerful punch. This, combined with the rising sea levels, will increase the severity of storm surge flooding in the future. But it's not just storm surges that pose a threat. Extreme rainfall is another major cause of flooding. In fact, in 1931, it led to the deadliest disaster of the 20th century, when prolonged rainfall, combined with melting snow, overloaded the Yangtze River in Asia. The local soil and terrain conditions amplified the effect, flooding thousands of square kilometers of land. Other factors, such as a dam failure and cholera outbreaks, were also major contributors to the extensive loss of life. That flooding took months to build up, but sometimes intense rainfall from a single thunderstorm can cause flash floods. These can also be very dangerous, particularly when the water contains debris swept along by the flow. When floods lead to structural failures, the consequences can be greatly magnified, as was the case in 1979 with the Machu Dam in India. So, could rainfall events also be affected by climate change? Well, a warmer atmosphere stores more moisture, so unfortunately the answer is yes. Already, rainfall records are being broken more frequently. As the intensity of rainfall increases, the chance of severe flooding increases too. Warmer conditions can also generate flooding directly by increasing the amount of melting snow and ice. This can not only overload rivers, but also weaken the banks of glacial lakes, causing catastrophic structural collapse and devastating flash floods. This happened around Lake Palcacocha, South America, in 1941. The severity of flooding doesn't just depend on the quantity of water, but the conditions of the soil. In some regions, increased temperatures dry the soil, allowing the ground to soak up excess rainwater. In other regions, infrequent, intense downpours cause the soil to become hard and impermeable, which creates the opposite effect and increases the chance of floods. So, going back to our original question, is climate change making flooding worse? Well, the factors affecting flooding are complex, but it's predicted that when floods occur, they are increasingly likely to be more severe in the future. Thankfully, there are ways we can minimize the impacts. Flood protection and barriers can be very effective defenses and have been added in many areas, particularly along the coast. Advances in technology allow many of us to have better weather forecasts and warning systems that give us more time to prepare. In 2021, for example, rainfall on the Yangtze River was even greater than it had been in 1931, but thankfully the loss of life was far less. Hopefully, these can improve further still and become available to all parts of the world. In the summers of 1936 and 1938, a small scout plane flew over the Arctic islands of Svalbard, photographing the terrain. The people on board had no idea how important the images they were capturing would be in demonstrating some of the most extreme effects of climate change anywhere in the world. To them, this was just a routine survey to create a map. They didn't know that much of the ancient glacial ice that they were flying over would soon be gone forever. For many years, the photographs sat in a drawer, forgotten. It was only 80 years later that they were rediscovered, and it was realized they contained enough detail for software to reconstruct the area as an accurate 3D model. This could then be compared directly with how the same area looks today. In front of you is a small part of that model. You can compare the 1930s reconstruction with how the same area looks now. The red areas highlight how much ice has melted away. From this comparison, we now know exactly how much the glaciers of Svalbard have declined, and this chart shows the result for the whole area. The blue shows where the ice has increased, and the red where it's decreased. For at least the past 150 years, most glaciers on the planet have been slowly shrinking. But in the last 40 years, the rate of melting has dramatically accelerated. Recent findings show that now almost all of the world's glaciers are retreating simultaneously, which hasn't happened for at least 2,000 years. Summer is the crucial time for glaciers. Most of the damage is caused by longer, warmer summers, melting more ice than's being replaced by fresh winter snowfall. Polar amplification has increased the rate of warming in Arctic areas. Svalbard is particularly vulnerable because there the rate is even faster, but many other areas are also badly affected. In just the last 40 years, the average thickness of the world's glaciers has reduced by 24 meters, the height of an 8-story building. In that time, an incredible third of the volume of New Zealand's glaciers has melted away. Since 1901, melting glacial ice has been a larger contributor to sea level rise than the ice sheets of Greenland or the Antarctic. If we lost all the world's glaciers, that alone would cause a global sea level rise of 0.5 meter. Even now, devastating flash floods can occur when melting walls of glacial lakes burst, creating a deadly wall of water that can engulf villages downstream. The loss of glacial ice removes a key source of seasonal meltwater that supplies fresh water for important wildlife habitats. We rely on this water too, for drinking and many commercial activities. Unfortunately, every future scenario shows that glacial retreat will continue, but reducing the global rise in temperature will help to reduce the rate of decline. This would have a big impact on the amount of global sea level rise. Whatever happens, photography will continue to play a vital role in documenting what was once there. "68% of the fresh water on Earth is stored in two giant ice sheets, thousands of meters thick, covering most of the surface of Greenland and Antarctica. These were formed from snow, becoming compressed over many centuries under the remains of the last ice age, a time when ice sheets covered much of northern Europe and North America. Over time, the ice, moving under its own weight, gradually flows towards the coast. This eventually forms ice shelves that float on the ocean. These in turn carve into icebergs and melt away in the relatively warmer oceans. New snowfall helps to replace the ice, but is this sufficient to prevent the ice sheet flowing away? Measuring the overall gains and losses is important because when the water from the melting land-based ice finds its way into the ocean, it contributes to a rise in sea level. Accurate measurements taken using satellites have found that the amount of ice is steadily declining, particularly in Greenland and Western Antarctica. As an ice sheet melts, its height reduces, which exposes the surface to higher temperatures at lower altitudes, causing yet more melting. This reduces the level even further in a vicious circle. Currently, this could be stopped if we halted the rise in global temperatures, but that may not always be the case. If this continues, it could lead to an irreversible decline, a climate tipping point. It is thought that for some parts of the ice sheets, this could occur soon with our current rate of warming. Preventing global sea level rise would then become an even greater challenge. In polar regions, the surface of the ocean is cold enough to freeze. The amount of this sea ice varies with seasons reaching a minimum in late summer. Satellites have been accurately monitoring the extent since 1978, and for the past 30 years, it's been dramatically declining in the Arctic. This is concerning because sea ice helps to regulate the planet's temperature. An ocean covered in bright white sea ice can reflect 80% of the sunlight that hits it back into space, whereas the dark ocean on its own can only reflect about 10%. The rest is absorbed by the ocean, causing it to warm. This in turn causes yet more ice to melt in a vicious circle. Many future projections show that by the end of the century, the Arctic Ocean could become completely ice-free in the summer. This may allow new trade routes to open up, though the effect on the rest of the planet would far outweigh any benefits. Entire ecosystems that currently rely on sea ice could be destroyed. Unlike the melting of land-based ice sheets and glaciers, melting sea ice would have little effect on sea level rise. This is similar to how a floating ice cube melting has little effect on the level in a glass of water. Around the Antarctic, The extent of sea ice has been much more stable than the Arctic for a variety of reasons, including how ocean circulation behaves in that area. Also, because there are no land masses near Antarctica, each year's ice can float away. Very little Antarctic ice remains all year round. During 2023, the levels of Antarctic sea ice were far lower than ever previously recorded. Forests are often called the lungs of the planet because they help to maintain the Earth's balance of carbon dioxide and oxygen. Actually, oceans play the biggest part of all, but even so, forests absorb approximately 30% of our carbon dioxide emissions. As trees harness energy from sunlight, they not only extract carbon dioxide, but also release oxygen into the atmosphere. Like wetlands, forests also help to maintain the balance of water in the atmosphere and ground. Trees can draw water from underground through their roots, releasing it into the atmosphere through their leaves. Without this, areas become drier, and this can prevent forests from regrowing again. A vicious circle. Also, without forests, rainwater doesn't soak into the soil as effectively. Instead, it runs directly into rivers, which can make flooding more likely. Despite the importance of forests, humans have so far removed a third of them to clear land, mainly for agriculture. Over thousands of years, most of the forests of Europe, North America, and parts of Asia have been destroyed, but in the last couple of centuries, the rate has increased, hitting a peak in the 1980s. Most deforestation now occurs in tropical rainforests, which is a major threat to nature's biodiversity. In 2019 alone, an area roughly the size of a football pitch was lost every 6 seconds. This extensive deforestation changes the local climate by both reducing local rainfall and increasing the chances of flooding. It also contributes to global climate change by reducing the amount of carbon dioxide being absorbed from the atmosphere. Globally, the more new trees that can be planted, the more this reduces the problem. Forests have an enormous environmental importance, but despite being much less well known, peatlands are important too. In addition to filtering drinking water for millions of people, they store up to twice as much carbon as all the world's forests combined. But when peatlands are drained or disturbed, their carbon is released back into the atmosphere. This contributes close to 5% of human-caused greenhouse gas emissions. And when the dried peat catches fire, the amount of carbon dioxide released can double. So, what is peat, and why are peatlands being destroyed? Peat is a type of soil formed when low oxygen, waterlogged conditions prevent dead plants from decomposing properly, preserving them like pickles in a jar. The plant's carbon is trapped within the soil, preventing it from returning to the atmosphere. Peatlands cover around 3% of the Earth's land surface and are found in almost every country. But since 1970, 35% of the world's peatlands have been destroyed. For centuries, people have been draining peatlands and extracting the peat to use as a fuel and for improving plant growth. Until recently, most people were completely unaware how much this damages the environment, with some serious side effects on people's health and well-being. When water's drained from peatlands, the peat soil starts to react with the air, releasing the carbon that's been captured and stored for centuries. The dried out peat becomes vulnerable to burning. Any ignition source will easily set it on fire. Since the layers of soil in peatlands can be very deep, fully extinguishing fires can be extremely difficult. In Arctic regions, peatlands are known to burn under the snow, undetected for months. Southeast Asia is also particularly affected by these fires, especially in the dry conditions enhanced by El Niño. In that part of the world, large areas have been cleared for agriculture, such as palm oil plantations. Cloud cover can make the true extent of these fires difficult to spot, but improved satellite monitoring now gives a more accurate picture. Recent estimates for the quantity of carbon dioxide released from these fires is astonishing. On some days, it's comparable to the amount released by the whole of Western Europe, China, or the United States over the same period of time. The smoke from the fires is a major health hazard and is thought to have caused many premature deaths. It seems obvious that restoring peatlands should be a priority, but there's a catch. Wetland areas contain bacteria that emit large quantities of methane, a greenhouse gas far more potent than carbon dioxide. Even so, methane stays in the atmosphere for a much shorter time, so in the long term, the reduction in carbon dioxide more than compensates for the increase in methane. Carefully managing water levels and the type of vegetation that grows there can greatly reduce this issue as well. Recently, initiatives have been put in place across the planet to restore large areas of peatland and prevent further damage. This should help to protect the natural world and combat climate change. When the climate in a location changes significantly, it can force its inhabitants to move elsewhere. This is particularly true for countries that can't afford to adapt to the new conditions. Recent sea level rise has caused the soil in low-lying areas to become salty, threatening the survival of any crops growing there. Other areas are in danger of becoming submerged altogether. Flooding is a threat that not only affects agriculture, but can impact urban areas too, particularly those located in coastal areas. At a rough estimate, more than 200 million people worldwide live along coastlines less than 5 meters above sea level. But by the end of the 21st century, this figure is estimated to increase to between 400 and 500 million. We're also seeing an increase in higher temperatures and drier weather, which can lead to long-term drought, another major agricultural threat that can force people to move elsewhere. But climate migration is nothing new. In the 1930s, the Dust Bowl in the southern plains of the US caused millions of people to face starvation. They were forced to move towards the west, rebuilding their lives in new locations, such as California. The problem had been triggered when farmers mistakenly removed deep-rooted grasses, not realizing they're vital for keeping topsoil in place. Years of prolonged drought and high winds then caused the topsoil to blow away, making the land uninhabitable. Unfortunately, current climate change is likely to have an even greater effect. A UN report states that there were nearly 10 million weather-related displacements during the first half of 2020 alone. The World Bank predicts that by 2050, there could be double the number of climate migrants as refugees in the world today. Fire is an important and natural part of life on Earth, and some plants actually rely on it for their survival. It limits the growth of competing species, and its heat releases their seeds. But it can take years for nature to recover from a wildfire. As the planet warms and humans alter the land, wildfires are becoming increasingly frequent, more intense, and now spreading to regions where previously they were rare or unseen. Hot, dry, windy conditions make vegetation vulnerable to combustion and help the fires spread. Fires which are often started by human activity. A discarded smouldering cigarette or a lightning strike is all that's required to start a fire that will burn through a vast area of land. Trees store carbon as they live and grow, but release massive quantities of it into the atmosphere as they burn, contributing to the very warming that will encourage yet more fires in the future. A damaging, vicious circle. It's important that forests grow back as quickly as possible. One way or another, we've been burning fossil fuels for thousands of years, rapidly releasing the energy that took plants millions of years to store. Centuries ago, the effect of this burning was insignificant, but this all changed during the Industrial Revolution, which started around 1760. Many countries dramatically increased their rate of burning fossil fuels. The prosperity this created led to a dramatic population increase, and this, in turn, generated yet more demand to burn fossil fuels, an unfortunate vicious circle. Originally, coal was the dominant fuel, and it's still the most popular for generating electricity. This is despite it releasing more carbon dioxide per megawatt than anything else. Oil is not quite as harmful as coal, and it's been vital to the development of the world we know today. Everything from transportation and heating to plastics and fertilizers have relied on oil. When used in power stations, natural gas only releases half the carbon dioxide of coal and oil, but this is still a major amount. It's not just fossil fuels that contribute to carbon dioxide emissions, though. Cement production releases huge quantities when the limestone source material is heated up. On the graph, it's in fourth place, but it's still a significant factor, contributing around 10% of global emissions. Ideally, the manufacturing process needs to change to capture all the carbon dioxide before it's released. Many organizations are prioritizing the reduction of carbon dioxide emissions, and efficiency improvements have already helped this process. The aim, though, is to move away from obtaining our energy from burning fossil fuels towards alternative green options such as wind and solar. Once these are installed, they would emit no carbon dioxide. Nuclear and hydropower offer non-weather dependent alternatives too, although of course they present other challenges for the environment. Whatever methods used, the proportion of energy production that doesn't rely on fossil fuels is increasing over time. In reality, it is likely that some of our activities will always need to emit at least a small amount of carbon dioxide, but emissions can be partially offset by increasing the amount of carbon dioxide that's captured again. This can be achieved by planting native forests and seagrass and restoring peatland, to name a few. Practical carbon capture technologies are being developed to mop up the excess carbon dioxide. While this technology is not yet viable, with investment and planning, it could be one day. If we capture the same amount of carbon as we release, the overall amount in the atmosphere will remain the same. This is what's referred to as net zero, and is now the target for many organizations. Climate scientists have modelled various possible future scenarios to assess how different choices and actions may affect the Earth's climate. They're designed to give an indication of the impact that changes in our behaviour would have on our future. In the projections section, we include 5 of the scenarios. That gives us a good representation of how much our future depends on the amount of greenhouse gas we emit. They have complex technical names, but essentially they refer to the amount of emissions we produce over time. So they're also known as very low, low, medium, high, and very high. Very low is the scenario with the biggest emission reductions. Here, the world takes a more sustainable path with lower energy consumption, phasing out fossil fuels, and less reliance on material growth. We managed to reach net zero emissions by 2050. This limits the warming the most. By 2100, globally, the average temperatures are kept within our 1.5 degree target. Low is like the previous scenario, but not quite as successful. We reach net zero by 2075, leading to average global temperatures reaching around 2 degrees Celsius above pre-industrial levels by 2100. Medium is much closer to the path which we've been on recently, with some places making more progress than others to improve sustainability. Carbon dioxide emissions fall, but don't reach net zero by 2100. Global average temperatures reach about 3 degrees above pre-industrial levels by that time. In the high scenario, regions compete for energy and food goals with large inequalities. Environmental issues are a low priority. In this scenario, compared to pre-industrial times, carbon dioxide levels double by 2100. This is currently considered a worst-case scenario that is unlikely unless recent progress is reversed. Very high was considered the worst-case scenario until about 15 years ago. Since then, most experts think this is no longer possible due to our continued progress in emission reductions. It's included here to give an interesting illustration of how much progress we've made and what could have happened if we'd ignored climate change. So, which path do you think we'll end up taking? See what could happen to the planet's climate as each scenario plays out. Climate Station has allowed us to gain a new appreciation of our planet's climate and how it's changing. The story continues to evolve. In 2023, the global temperature suddenly surged. It was warmer than any previous year ever recorded, only to be surpassed by 2024, which exceeded 1.5 degrees Celsius above pre-industrial levels for the year. Remember that most of the heat is stored in the ocean, hiding the true scale of the problem. On our current course, by the end of the century, the planet will have warmed by nearly 3 degrees since pre-industrial times. Heat waves, droughts, and heavy precipitation will become more frequent and intense. Tropical cyclones are more likely to generate devastation on the scale of Hurricane Dorian, as shown here. The consequences will affect everyone. But this doesn't have to be our future. We know what's causing the problem. Burning fossil fuels has released millions of years of stored carbon back into the atmosphere, causing it to heat up. Meanwhile, we've destroyed natural features such as peatlands and forests that would have helped to recapture this carbon. The Paris Agreement set out a goal of net zero emissions by 2050. The amount of carbon we release should be balanced by the amount we capture again. This would reduce warming by the end of the century to 1.5 degrees, far less damaging than the 3 degrees where we are currently heading. We've already come a long way and rapidly adopted green energy technologies. About 15 years ago, climate research indicated we were heading to nearer 4 to 5 degrees of warming by 2100. So, there is still hope. But hope is delivered through action, and we need to act now. We need to reduce the amount of fossil fuels we burn as much as possible, switching to renewable energy. We need to restore and expand natural features such as peatlands, forests, and seagrass to capture the carbon that we do emit. Everyone needs to play their part. This is true for us as individuals and as communities. We can encourage industries and nations to play their part too, by the choice of organizations that we support. There are 8 billion of us on the planet. It's all down to the choices we make. How we travel, how we heat our homes, and what we consume. The challenge is to ensure that as many people as possible understand the situation we're in. This is the first step towards positive change. Everyone's contribution to limit further warming will make a difference. Every fraction of a degree matters. Our introduction to Climate Station is now complete. You're now welcome to continue your journey and discover your very own climate story.